Good morning, Year 12. Good to see you guys. It's really great to see you guys attending. It's really nice. It's also really good to see you too. Let's turn that off. Oh, nuts. I've just totally ruined that. I was all set up. Oh, hang on. Pause, mute. There. Go, wait, stop. There we go. Julian, thanks very much for trying to contact them. That'd be really, really useful. I need to do the register. It's good to see you, Dinesh. Thanks for coming. Thanks for coming, Tenzi. Right, today's lesson, I'm pretty much going to crack on as quick as I can. So I'm going to do share screen. I hope you guys are all staying well. Obviously, in this trying time, it is difficult. Right, just going to do that now that you guys can see my screen. I'm just going to disable my camera because the problem is it runs in the background, you see. And if I do this, it gives me a little bit more time before it goes all shaky on me. So, okay, so today's lesson, we're cracking on with alkanes. So today we're doing a cracking lesson. I need to stop with these dad jokes. Honestly, it's not really my fault. I'm taking medication for it, so don't worry. So we're going to be looking at cracking today. So learning objectives for today. Learning objectives include. So we've got. I need you guys to be able to write equations. Write equations for cracking. I need you to be able to understand the differences. Do you know what? Actually, it's actually rather than the differences, understand thermal cracking versus catalytic cracking. I've suddenly realized if I just do this, if I can just, you see, oh, brilliant, well done, Mr. Duncan. I love how my laptop just randomly loses letters. It's amazing. Thermal versus catalytic cracking. Like it. There we go. Amazing. Do we have them hit win kits here? Woo! Who's Maggie Crack? Who is that? Is that Dixon? Oh my goodness me. Cool. That means I can finish my register. Whoop whoop. I think I've got all of you now. Yeah, that'll do. Okay, cool. So you guys need to be able to write equations for cracking. That's easy. That's GCSE. You guys can already do this. Yeah, that's GCSE. So I put that first just because I do realize that you guys can already do it. So you should be able to do this one already. That doesn't look like a tick. There we go. Tick. But we will look at some exam questions of those as well. But understand the differences. And I need you guys to know the setup diagram. Now, I've actually included the two setup diagrams that have been in papers recently. Can I just say that these setup diagrams are usually paper 3. So these diagrams, which you can see kind of making a little sneaky inroad over here, that really is paper 3. That's for the practical paper. Okay, and we'll talk about those in more detail in a minute. I am going to say, by the way, just remind me, guys, that we did the combustion of alkanes last lesson, and I'm very aware that I didn't cover the catalytic converter for cars, and I hope maybe I might be able to tie it into today's lesson, but it's something that I feel like I might have missed. I know that Edexcel don't ask it very often, but I'd still like to do it anyway. Okay, so let's do some writing equations for cracking. This is GCSE. So this is technically GCSE Chemistry, and we can do cracking equations. Oh, I just can't stop it, you know, guys. I'm so sorry. So, and I just want to show you that these do come up on a regular basis. So this is just a booklet of AS level organic questions. And it's nice for me to say, so we've already done name the process to separate fractions, fractional distillation, give the formula of an alkane with 9 carbons, nice and easy. Write the equation for complete combustion of undecane, nice and easy. Write the equation for the incomplete combustion of undecane to produce carbon and water only, particulates, global dimming. Write the equation for thermal cracking. Right, guys, there's your question. Can you please pause the video Pause the video and have a go at it for me. Can I have 1, 2, need a pen? Oh, have a go at that for me, guys. I'm trying to think of how I remember doing the snip. Oh, I've lost my snip function. I didn't want that. That one, please. Snip. That's what I want. I want you, snip. There we go. No. And I'm going to go, cha. Oh, I've cut the top off. No. Let's try that again. There we go. So I want you guys to have a go at this. Copy and paste. I'm so cool. It's crazy. There we go. So this is, I said, straight out of GCSE, not complicated. Don't want you guys to overthink this. Please don't. You don't need to. But what's going to happen now is, of course, at GCSE, they did ask these actually. Edexcel did like to. But what they're doing is, right, they're putting in decane, 1 molecule. Bear that in mind. They could have said 2. Be careful with all these little details. 1 molecule. So I'm going to put in C10H22. Right, arrow. Now, just remember, cracking, the conditions for it, high temperature, well, in fact, I'll put that into thermal and catalytic in a minute, but no air, that's the key thing for this bit. So 1 molecule to form propene. So I've got C3H, and it's an ene. So I need to just double it, CnH2n, and 1 other molecule, an alkane only. So now all we need to do is look at the atoms which are left behind. I've got C7 left, and I've lost 6 H's there. I've lost 6 H's, so how many am I going to have left? 22 minus 6 is 16. 16. Is that correct? Double and add 2? Yeah, that sounds about right. There we go. So not a complicated question. Not complicated. I want to show you one that's slightly more challenging. See if I can find another one of these. They will be. They'll be around. Let's see if I can find another one. There's the catalytic converter, you see, guys. There's the catalytic converter. Very aware of it. Oh, state property, cracked. Write an equation to produce, that's combustion again. Give one reason, catalytic cracking. Write an equation for the complete combustion. Crude oil fractional distillation. I'm looking for a cracking equation. Conditions, coming to that one in a minute. Hydrocarbons. Write the molecular formula of the alkane with 19. That's fine. There it is. Okay, guys. Again, technically GCSE. Oh, I didn't want to do that. Technically Technically GCSE, guys, but much harder. Much harder. This is much more challenging. Let's see if we can have a look at this one. I'm busy. I know it's not really ideal. As there we go. Shrink that down, lob that there. Much more challenging. Right, guys, pause the video. No need. Okay. All right. Still on the pen thing. So write an equation for one possible cracking reaction of the alkane 616H when the products include ethene and propene in a molar ratio of 2 and one other compound. Much higher. Pause the video. Have a go, please. Right, here's your answer. So C16H34. Right. Okay, so now we need to produce ethene and propene. C2H4 for ethene. Propene, C3H6. In a 2-to-1 ratio, and the 2-to-1 applies to these guys. So 2 ethenes to 1 pro. So 2 of those and 1 of those, and one other product. Right. You realize this is not complicated, is it? Year 12. Yeah. This is simple, basic maths. This is literally like year 5 maths. So how many carbons are there? 4. How many carbons are here? 3. Total number 7. So I've got to then take away that 7. So I'm going to end up with C9. H, right, what's left now with my H's? I've got 8 hydrogens here. I've got 6 hydrogens here. Total number 14. Take that away, it's going to be 20. There we go. So there's my final answer. So you can see that just they're just making it complicated. Lots of students might freak out because of the words molar ratio. Please don't, no need to. It's not overly difficult. Right, so at this point, we can now go, we can do equations, definitely, double tick. Yeah, next. Right, we need to now talk about thermal and catalytic cracking. So let's zoom in, let's go. Let's talk about catalytic first, because catalytic you've already done. You just don't realize it. So catalytic cracking is GCSE cracking. That's all this is, folks. The reason being is we're using a catalyst. So here's the setup from GCSE. Here's the diagram that you guys need to know. So this is the one most commonly seen image. I'm very sorry, Year 12, about the quality of the quality of the picture. I couldn't find a better one. I tried to get it properly off Google, and it was just saying, the site is down for maintenance. I currently only have one person watching. Are you guys still there? Can you guys still hear me? I'm just worried in case there's a reason that it's saying only one person watching. But this is the diagram. So, by the way, you guys, yeah, the porcelain chips are our catalyst. However, you're not allowed to call them this. So what you guys have to, this now gets replaced to, that's really weird. That's very strange. Sorry, my laptop's having a slight paddy, and I don't quite know why. I don't know why it's struggling with this, folks, but it is. I don't know. Oh, it really is having problems. Let's see if I make this, I think that should already be. I don't know why all of a sudden it decides to do this. It's suddenly gone, no, I'm going to go really slow. Oh. Uh-oh. Sorry, folks. Hang on. My tablet is being rather odd right now. It's doing some very strange things. Having technical difficulties. What I'm going to do is I'm just going to close that down for a second. My laptop is just having a mare. I'm so sorry, folks. I'm having technical difficulties. Who is that one person? No, I can't, unfortunately. My laptop has decided to go absolutely stir-fry crazy. It's completely frozen, folks. I'm very, very sorry about this, guys. Don't know why. Oh, dear. Do you know what? You know, you use modern technology. I don't know quite why. It's not letting me do anything, folks. I'm really sorry about this. All it's doing is letting me zoom. My laptop won't close. It's got, I don't know why it's having a complete freak out. I'm so sorry, folks. It's Mr. Duncan. I don't know why it's doing this. My computer's having it's frozen, guys. Right, I'm going to have to, is Chrome taking too much? Yes, possibly. I don't know why. This is meant to be a really good laptop, and it's just really not doing me any favors recently. Unfortunately, guys, I've completely frozen. So what I'm probably going to say is, it just won't let me do anything. It's completely stopped. It's still letting me write. So I'm just tempted just to zoom in on another area and start writing. If I can. There we go. I'm just going to continue writing, folks. Oh, it won't even let me. Okay, so won't let me do anything other than, it's back. Go figure. So sorry, folks, about this. So the setup that you guys saw momentarily ago, sorry about that, Check Task Manager. I know I don't know quite why it's struggling so much. I'm going to try and clear some of this memory out, but I don't think it's really, the memory is not the issue. So catalytic cracking. What you learn are the 4 C's. This is the 4 C's. I'm going to reduce my pen size now. 4 C's of catalytic cracking. I'm just going to get the details down. Catalytic cracking. And those 4 C's, number 1 is you need a catalyst. That kind of makes sense, doesn't it? Yeah. And the catalyst, you guys have to now know the name, which is called zeolite. You are actually allowed to quote the GCSE answer of aluminum silicate. That's actually allowed as well, but they want zeolite at A level. The next thing is the mechanism is it goes via what's called a carbocation mechanism. Now you need to know nothing about this, folks. I'm actually going to give you a little bit more detail though, because I'm going to start introducing mechanisms in this particular lesson. The next thing is you form cyclic compounds. Cyclic compounds as a high percentage. High percentage cyclocompounds. And these are used for car fuels. This is catalytic cracking. We do catalytic cracking to produce car fuels. Because you get cyclic compounds instead of alkenes. It's nice for me to just expand on this bit here and go functional. We've already done this in one of my webinars. Functional isomers. There aren't many at AS that you guys need to know. Is it just my site that keeps refreshing? I have no idea. Mine's letting me zoom and it's doing all kinds of weird things. But functional isomerism, you guys remember that alkenes, so this is propene, alkenes have functional isomers of cycloalkanes. Now, you guys need to know that the cycloalkanes are actually better fuels. They have lower boiling points due to, we know that if you add a branch, you reduce the surface area, therefore you reduce the van der Waals forces, therefore you reduce the boiling point. So cycloalkanes are great fuels, and you don't produce many alkenes. Now, because you don't produce many alkenes, of course, that means you're not going to be using this for polymerization. Again, my laptop's having slight issues. There we go. Trying to cope with it as best I can. Okay, just to explain the carbocation mechanism, when you have a catalyst with cracking, and the catalyst is zeolite. Now, what's happening is we're adding heat all the time to this as well. We're adding heat to this. So the alkane, the long alkane, I'm going to put in a long alkane here, like this. The long alkane will be passing over the catalyst. Now you'll notice I've put the hydrogens on one of the carbons on one side. There is actually a reason for this. The reason why, what happens is the catalyst rips off a hydrogen. This is because zeolite has a really cool structure. It's got like these pores in it. If you want to look that up, you can do. It has these holes in it. It's like almost got like a hexagon. It's not quite a hexagon. It's actually rounder than a hexagon in reality. But what happens is, in fact, I shouldn't really put the two hydrogens on a side. I should just keep it like this. But what's going to happen is the catalyst takes a hydrogen off. It actually completely binds to it. But it rips that. I'm going to actually draw a pen line and say it takes the hydrogen completely off with its electrons as well. What that means is the catalyst causes the formation. So for a moment, we have the, by the way, you don't need anything or any of this detail, guys. You do not actually need to know. But what you now temporarily form, very briefly, I'm not going to bother drawing the rest of it out. I'm not going to bother. But what you're going to actually form is what's called a carbocation. And that's just a carbon, which is a fully positive charge. This, of course, makes it very unstable, and the whole thing now breaks. The electrons move. I'm going to do the curly arrow on the other side. Those electrons now go in that direction to compensate. And that hydrogen on the end is, that carbon on the end is then going to take the hydrogen back. But that's all you need to know. Just these words here, carbocation mechanism, that's it. Carbocation, by the way, is actually a single continuous word, but it doesn't really make any difference. I like to separate it, suggesting carbon and cation being the positive ion. So that's what we need to know for catalytic. What we now need to know is the conditions. And we can add the conditions on to the first one. So this one here is your conditions. Conditions. I don't know why my laptop's doing what it's doing. Condition. So we've got catalyst, which is zeolite, and we've got a temperature of 450 degrees Celsius. So at that temperature, no air as well, no air. If there's any air, it's just going to combust. Zeolite catalyst, 450 degrees Celsius, no air. Those are our conditions. Carbocation mechanism, cyclic compounds in a high percentage instead of alkenes, and these go into car fuels. This is a really handy set of the 4 C's of catalytic cracking. And again, let's have a look at our diagram. Oh, sorry about all this. My laptop does seem to be at least functioning ever so slightly. So I found this one on an A-level paper. I love the fact that they have this extra piece in here, because what they're showing is they've got the aluminium oxide or broken porcelain. You guys are now, of course, going to call that zeolite. Notice that you've got to provide, it's warm here, but then strong heat here. The reason being is we're breaking carbon chains. This is at this point here, we're going to boil the alkane, turn it from a liquid to a gas. It needs to be a gas to break it. And at this point, we're providing the heat because the catalyst needs to be hot, increase the rate. This is to break covalent bonds. Break covalent bonds. And of course, it's going to break the CC bonds. And it doesn't break the CH bonds. The reason being is that has a bond enthalpy. Running out of space. The bond enthalpy is 348 kilojoules per mole for the CC, but 412 kilojoules per mole for the CH bonds. So, by the way, don't quote me on those numbers. They might be wrong. It's what's in my head. But I mean, I'm just spitting them out rather than looking them up, and I'd always look them up in reality. But we always break these guys. We don't break the carbon hydrogens because this value is lower. Weaker bond, more likely to break. Yeah, weaker bond. Okay. They're going to ask you what's the function of the cold water. We're condensing. This is down here. This product here, A, is going to be the shorter alkane that's been made. And B, of course, is going to be your short. This is going to be your short alkene. However, we're going to get that in low percentage, but we've also got a short or small cycloane as well in a high percentage. So that's what we're collecting in that particular one there. Okay. And the water, of course, the cold water is there to condense it. You can add that to your notes if you like. In this diagram, this one's much more common. This one, because they haven't bothered to condense the shorter alkane. The shorter alkane, by the way, will tend to just pool in here. Yeah, but we're collecting the gases here. And again, product gas. So we're going to have a short alkene and a mixture of cycloalkanes as well in higher percentage. By the way, problems with this practical. Again, paper 3 is about often talking about problems with these things. I've seen all kinds of funny variations on this diagram. One, I've seen diagrams where the cork hasn't fit properly. I could probably draw you a version of that, where you see the test tube here and the cork is like this, which is really stupid. It says, what's wrong with the diagram? And you go, because the gas is going to escape because the cork didn't fit. Yeah, seen that before. Other problems, of course, is suck back. It's one of the key problems with this practical. You never collect, so little details. These are nota benes, really. So number one, we don't collect gas at the beginning. Don't collect gas at start. The reason being is it's just air. Yeah, it's just expanded air. As you heat it, the air expands, so you produce air at the beginning. It's not hot enough to do so. The second one is we get suck back. So suck back. Suck back is when, if they stop heating, Stop heating before removal of water. Removal from water. And what's happening there is, I'll just zoom in on the section there. So because the delivery tube is underwater and we're collecting the gases a bit like this, and the bubbles, the water's here. Yeah, water's there, and the gas that we're producing is going up here. Well, if you leave the delivery tube underwater and you stop heating it, what will happen is that the air will start to cool and it will start to contract, which means water will start to move up the tube. It'll slowly get sucked up, and if it hits the test tube, it can explode. So it's something as I said, they do often mention it in practical exams. How can you prevent it? Remove from water before you stop heating. Not complicated. Cool. Okay. So now that we've spoken about catalytic cracking, in terms of economics, by the way, another question. By the way, you never in chemistry, in any of the chemistry exam, do we need both diagrams? Both, that's a really good question. And if they asked you to draw it, you would draw that one. That's the one you would draw. Yeah, it's simpler. You don't need the Bunsen burner, by the way, in your diagram. You just put it as heat. But they have given you both of them in the past, just so you know. I am very aware it's very easy as a teacher just to say, draw this one, learn that one. But in reality, they can give you these all kinds of bizarre ones. And as long as you're able to deal with it, it's better for me to have talked it through with you guys than to just be blindsided by a setup that you'd be like, why have they added this on? Yeah. And so I'm teaching it, but drawing them in reality, no, you can just draw the second, draw the easier. Okay, so the next bit, just to say, in chemistry exams, you never, ever, ever mention cost unless they say, this is a nota bene. Yeah, this is nota bene. Never mention cost. Never mention money. I'll put money stroke cost. Unless you see the word economic. Unless economic is in question. I'll show you what I mean. I saw one briefly up here. Catalytic cracking. Name a catalyst using and outline the industrial conditions used in the process. So the catalyst is zeolite. The conditions are no air, 450 degrees Celsius. We're done. By the way, you do it under low pressure as well. Not low pressure, but just kind of 2 atmospheres. It's not done under a huge amount of pressure. They just want the temperature really in that particular case and no air. Give the 2 main types of product from catalytic, a shorter alkane and a cycloalkane. Yeah. Use the data. Use the data given to explain why catalytic cracking is important. Right. So people are going to say money. No. You never ever mention cost or money unless they say the word economic. We're doing it because the demand for petrol, the supply for gases is low and the demand is high. And look at this one. Global petrol and naphtha, supply is low, demand is high. Kerosene, supply is high, demand is low. In this particular question, we're going to crack kerosene to make these guys. Yeah. The supply is being exceeded by the demand. That's why we crack. Nothing to do with value of cost. I'm trying to find one where it actually mentions cost. There is one. I saw one. There you go. State one economic reason for cracking of petroleum fractions. So you now must mention value or cost. And in this case, it's going to be that the value of the shorter chains is higher than the longer chain alkanes. We're done. Yeah. Winkit, did I explain your suck back question? Anyway, so going back to this. Okay, so now that we've covered catalytic, we now need to talk about thermal. Thermal cracking. Now you see that I've underlined the E. Now guys, I've been underlining that E since I was in school. Yeah, the reason being is because guess what we make now? If you put in a long alkane, thermal tells you that this is going to be done via temperature, folks. There's no catalyst here. We're going to heat that long chain. We're going to produce a shorter alkanes, and I'm going to put shorter alkanes and high percentage alkenes. So it's nice to see that there's two different types of cracking and they produce different products. So let's now do the bullet points for this one. So number one, we've got number one, conditions. So the conditions for this are going to be high temperatures. Now the problem is that's not enough. You've got to quote one. And this one's an easy one. 1000 Celsius. That'd be crazy high, folks. And no air. Dead easy. Yeah. High temperatures, 1000 degrees Celsius. You've got to know it. And no air. Next. Products is a high percentage alkenes, and the mechanism is what's said to be homolytic fission, or a free radical mechanism. I'm going to show you what this is because you do have to know this one. So a free radical mechanism for cracking, what's happening is there's no catalyst now, folks. So here's what's happening. I'm just going to take a section of a chain. Once again, we're going to heat this up. We've got to be quite careful with the temperature now because, again, we're wanting to break this guy and not the carbon-hydrogen bonds. So we're being fairly specific on the temperature. If you go much higher, you hit 1200, you start creating hydrogen gas, not what we want. Very dangerous. But what we're now going to do is we're going to heat this at 1000 Celsius. And what's going to happen is we're going to break a carbon bond, and we now see for you guys possibly your first curly arrows. And you get a very unusual curly arrow, which is this one. It's called the half head or fish hook arrow. There we go, that's better. Now, this arrow is very unusual for you guys. You're never, ever, the chances of you're never going to use this in an actual mechanism. This is the only place you're going to see this, folks. Yeah, that arrow is a very unusual one. And this shows the movement of one electron. I'm going to come back to this when I'm doing mechanisms in my next webinar. I'm going to be coming back to this. And it's actually really important that I do. Shows the movement of one electron. What that means is, if we were to zoom in on this picture, if we were to zoom in, on this, we've got one electron here and here. And what's happening is, when this is split, it's being split what's called homolytically. This is called homolytic fission. Now, the word fission, the word homo means same, we know this. That means same. The word lytic means to split. Yeah, this is the same splitting. But it actually means the same splitting products which is, and the word fission means to split in half as well. That comes from physics, homolytic fission. And what we're going to produce from this is we're going to produce two people. We're going to produce, and both of them are now going to be what are called free radicals. I'm actually going to show both of them with a dot because you never do it with the cross. These are your first time you're probably seeing free radicals. And a free radical, we can define this. A free radical, this is a nota bene again. I'm actually going to make my pen a bit thicker at this point. So nota bene. The definition of a free radical. A species. Notice the use of the word species. This a species, I prefer a. A species with an unpaired. You can't say one. An unpaired electron, which is what that dot represents. Anyone else lagging? Me from the start. I'm so sorry, folks. I feel like it's my fault. Is the video not looking too good? No. Oh, I'm gonna mute that. I'm gonna mute that and see if I don't know whether or not it seems to be going all right on this side. I'm sorry if it is lagging. I do apologize. An unpaired electron. So this is for thermal cracking. We get this at very different conditions, different temperature, a different set of products, and a different mechanism. That is all you need. If you're going to do this practically, you would have exactly the same setup, but you just remove the catalyst. You cannot do this in a lab. The reason being is at these temperatures, you're probably going to start melting equipment. You're going to start you probably won't melt the Pyrex boiling tube, but you're certainly going to start melting rubber bungs. You're going to be melting the soda glass delivery tube. You've just got to be really careful. That's hence we always do catalytic in class. We never do thermal because it comes up with a whole load of other problems practically. So we just tend not to do it. Going back to, it's nice for me to look at the specification here, folks, as well. So just coming down to here. Alkanes fraction, there we go, cracking. So we've got, I can't even highlight it annoyingly. It says 4.12. Know that alkanes of fuels can obtain fraction cracking and reforming of crude oil and be able to write equations for these reactions. Yeah, and then it goes practical. Cracking alkenes by thermal decomposition, including liquid paraffin using aluminium oxide as a catalyst. So Edexcel are not wanting you really to use zeolite. They're wanting you to actually quote aluminium oxide. That makes things a little bit easier. So something to bear in mind. Right, it's now 11:20. That brings us to the end of cracking. Just to identify the catalyst, use the aluminium oxide now. Identify the different types of hydrocarbons. Is there any other questions here that would be useful? 2-to-1 ratio, giving the lowest boiling point, branch it as much as possible. There we go. Give the formula of the alkane on cracking forms as the only products 2 moles of oh, that's clever. Let's just snip that one. I like that one. Ooh, that one's nice. Let's snip it. Oh, I don't want you. I want you. Snip. I'm going to put that tool, of course, onto my thing. If I go to new, I like that question. That's clever. I'm also going to take this one as well. Oh, refer to the table. Yeah, I don't know. Right. Edit. Copy. I think I have hyperlinked in this booklet, by the way, folks. If I haven't, please let me know. Let's go paste. If it'll let me. There we go. Paste. There we go. So let's zoom in on that one. Let's get to that. There we go. So give a molecular formula for each of the following components of crude oil. The alkane on cracking forms as the only products 2 moles of ethene C2H4, 2 moles of them, and 1 mole of butane, C4H butane, double it and add 2, 10. Right, put it back together, folks. That's all you have to do here. Put them back together. So I've got carbons, 4 plus 4. So I've got C8. How many H's? 8 plus 10. So 18. And we're done. There's my answer. Clever question. Getting you to reverse it. I think that's really neat. Anyway, I'm going to end my lesson there and see if I can bring you guys back. Let's see if I can bring you guys back. I'm going to re-enable my video because by the way, it's actually enabled device. It still hasn't helped. My screen is still shaking away. But there we go. If I do this and then go start camera and then click on that one. There we go. Right, guys. That brings us to the end of cracking. Have a go at the booklets on the classroom, on the worksheet, on the spreadsheet that I created. You guys know where they all are. Let me know how you get on. If you've got any questions, do let me know. I'm trying to incorporate as many of those exam-style questions into the lessons as possible just to help build that understanding. But keep working hard, guys. I know it's a difficult time. Look after yourselves. Stay safe. And I'll see you guys very soon. Catch you later, guys.